Have you ever wondered how computers understand and execute instructions? The secret lies in a fascinating language called machine code, a language that's as elementary as it gets. Machine code is the lowest level programming language, the one that is directly executed by a computer's central processing unit or CPU. Let's picture machine code as a series of binary instructions, a sequence of zeros and ones that the CPU can directly comprehend and execute. Each instruction in machine code corresponds to a specific pattern of these zeros and ones, a pattern that is directly understood and acted upon by the CPU. But here's the interesting part. Machine code is not a one-size-fits-all kind of language. It's specific to the computer architecture and is unique for each type of CPU. This means that the machine code for an Intel processor would differ from that of an ARM processor. When we talk about machine code, we're delving into the very core of computing, the fundamental operations that a CPU can perform. These operations are elementary, basic instructions such as arithmetic operations like addition and subtraction, data movement like load and store, and control flow operations like branching and jumping. The encoding of each machine code instruction represents a specific operation, source and destination registers or memory addresses, and additional information such as immediate values or offsets. This encoding is what makes machine code highly efficient yet intricate. Machine code's low-level nature gives it a direct correspondence to the hardware architecture. It provides a level of abstraction just above the hardware itself, making it a powerful tool for tasks that require direct hardware control or that need to be highly efficient. Although machine code offers the highest level of performance, it's not typically the first choice for software development. Writing programs directly in machine code is highly impractical for humans due to its complex and error-prone nature. That's why most software development is done at higher levels of abstraction using programming languages like C, C++, Java, or Python. These high-level languages are then translated into machine code, providing a more human-readable and portable way to write software. So, machine code is the computer's native language, a series of 0s and 1s that the CPU translates into operations. Now, you might be asking, what does machine code look like? Let's dive into that. Machine code instructions are represented in the binary system, the language of zeros and ones. This binary language is directly understood by your computer's central processing unit, or CPU. Each specific pattern of zeros and ones corresponds to a unique instruction that the CPU can execute. Now imagine a vast toolbox. Each tool in this box represents a specific instruction that the CPU can perform. This is what we call the basic instruction set. It's composed of fundamental operations that the CPU can carry out. Think of it as the ABCs of machine code. In this toolbox, you'll find arithmetic operations. These are like the mathematical wizards of the instruction set. They perform tasks such as addition and subtraction, multiplying and dividing. They carry out these computations on the data stored in registers and memory, essentially crunching numbers at lightning speed. Next, we have data movement instructions. These instructions, like skilled librarians, meticulously load and store data, moving it between the CPU's registers and the computer's memory. They ensure that data is always in the right place at the right time, ready for the CPU to process. Then there are the control flow instructions. They are like traffic police, directing the flow of operations within a program. They make decisions, perform loops, and jump from one point in the program to another based on specific conditions. They ensure that the program runs smoothly, taking the right path and making the right decisions. These are just a few examples of the many types of instructions that make up the basic instruction set of machine code. Each instruction, represented by a unique pattern of zeros and ones, tells the CPU exactly what operation to perform, providing the blueprint for all the magic that happens inside your computer. In essence, machine code instructions are the most basic operations that a CPU can perform. How does the CPU understand these binary instructions? Well, it all comes down to instruction encoding. This is the process of translating a series of operations into machine code instructions. Each instruction is encoded to represent a specific operation, and this operation could be anything from a simple arithmetic function to moving data or controlling the flow of the program. But it's not just about the operation itself. The encoding also tells the CPU where to find the source and destination registers or memory addresses. This is crucial because it dictates where the CPU will retrieve data from or deliver data to. The encoding can also contain additional information, such as immediate values or offsets, which provides the CPU with extra details that are necessary to execute the instruction correctly. Now, here's where it gets interesting. Machine code isn't a universal language for all computers. It's highly dependent on the architecture of the CPU. In other words, different CPUs have different instruction sets, and machine code for one architecture isn't compatible with another. Think of it like human languages. Just as English, French, and Mandarin have different words, grammar, and syntax, different CPU architectures have different binary instructions, encoding methods, and operational specifics. So, an instruction that works perfectly on one type of CPU might not even be understood by another. This is because the binary patterns that represent each instruction are unique to each architecture. The CPU will only understand and execute these instructions if they're encoded in its specific language. This specificity can be a double-edged sword. On one hand, it allows each CPU to be highly optimized for its particular set of instructions, which can lead to improved performance. On the other hand, it means that software written for one type of CPU can't be directly transferred to another without being recompiled or rewritten. Therefore, machine code is like a unique language for each type of CPU. Why don't we program in machine code then? Well, it's because machine code is inherently low-level, providing a level of abstraction just above the hardware itself. This means that each instruction directly corresponds to a specific hardware operation. Understanding these operations requires an intimate knowledge of the CPU's architecture, which is beyond the reach of most programmers. But it's not just about understanding. Writing programs directly in machine code is a complex, error-prone process. Imagine trying to communicate complex ideas using only basic building blocks of language, like individual letters or phonemes. It's possible, but it would be extremely tedious and prone to mistakes. Similarly, machine code is made up of simple instructions like load, store, and add. Combining these to create a functional, efficient program is no small feat. The complexity and potential for errors make it impractical for humans to write programs directly in machine code. Programming in machine code is like trying to write a novel using only the alphabet. So, how do we make programming easier? Well, we introduce the concept of assembly language. This is a higher-level representation of machine code that uses understandable mnemonics to represent instructions and symbolic names for registers and memory locations. This makes it a bit more palatable for us humans. But how does this translate back into machine code? The answer is through an assembler. The assembler takes our assembly language and translates it back into the binary 0s and 1s that the CPU can understand. Now here's the real kicker. The execution speed of machine code is unparalleled. Remember, machine code is the native language of the CPU. It's executed directly without the need for translation or interpretation. This makes it the fastest form of code execution. So, in essence, assembly language is the bridge that makes programming closer to human understanding, while maintaining the speed of machine code. What are the challenges with machine code, you might ask? Well, let's dive right into it. First off, debugging machine code can be a real head-scratcher. Unlike higher-level languages, machine code doesn't come with a friendly interface, high-level constructs, or symbols. It's just a series of binary instructions, and if there's a problem, it can be like looking for a needle in a haystack. Debugging tools are often employed to interpret and display machine code in a more human-readable format. These tools become a programmer's best friend, helping to translate the inscrutable binary of machine code into something a little less alien. But even with these tools, debugging machine code is no walk in the park. It requires a deep understanding of the CPU architecture and a keen eye for detail. It's a bit like being a detective, but instead of solving a crime, you're tracing through binary instructions, trying to find where things went awry. Now let's shift gears a bit and talk about another significant challenge with machine code: portability issues. Because machine code is so intimately tied to the specific architecture of a CPU, it's not something you can just pick up and plop down on a different machine. Different CPUs have different instruction sets, and machine code for one architecture is not compatible with another. This means that a program written in machine code for one type of CPU would need to be recompiled or even rewritten to run on a different CPU. As you can imagine, this isn't very practical, especially in today's world where software often needs to run on a variety of different devices and platforms. Despite these challenges, machine code remains an essential part of how our computers function. It might be a bit mysterious, a bit challenging, but at the end of the day, it's the language that our computers speak. And as programmers, it's our job to understand and work with it, no matter how tricky it may be.